Okay, welcome back. Let's continue. So this is our sixth lecture. The topics for today are the exponential family. It's a family of probability distributions, and the generalized linear models, or GLMs. The two topics are kind of tightly coupled, so we covered them in the same lecture. And before we get started, a quick recap to kind of see the motivation for exponential families and GLMs. So we've seen two models so far, a regression model and a classification model, and they were linear regression and logistic regression, right? And for both the linear regression and the logistic regression, we saw their probabilistic interpretations. And for the linear regression, the assumption that we made was y given x is sampled from a normal distribution with mean theta transpose x and some variance sigma square. It did not matter what sigma square was, and that's fine. In the case of classification, y given x was sampled from a Bernoulli distribution whose parameter was 1 over 1 plus e to the minus theta transpose x, right? And this was also, we call this g of z equals 1 over 1 plus e to the minus z, and g of theta transpose x becomes the parameter of the Bernoulli distribution, right? And then we had a small aside, mostly a digression in terms of what we're going to cover today, but this is going to be useful next week. Think of functions as points in an infinite dimensional functional space, and you kind of get a one-to-one mapping between the domain of the function and the axes of the functional space. Anyway, so this is not relevant for today, but just kind of keep this in the back of your mind. So we're going to continue along the lines of the probabilistic interpretations, and we're going to cover generalized linear models. So off the bat, we see a few things that are common between these two. All right. First of all, we are modeling y given x in both the cases, right? The difference is that in one case y is real valued, and in the other case y is binary valued, 0 and 1. And the data type of y, whether it is a real valued or a discrete binary valued, informed our choice of the distribution that we used, right? It doesn't make sense to define a Bernoulli over real valued. Similarly, it doesn't make sense to define a normal distribution on discrete valued. So the choice of the data type of the y variable informed the choice of the distribution that we used. The other thing that we see in both of these is the occurrence of theta transpose x. Right? We have a theta transpose x here, and we have a theta transpose x here, right? And these two seem to be somewhat superficial similarities, but what we'll see today is that there's actually a much deeper and richer theory that kind of unifies these two and a lot more different kinds of models under a common umbrella, right? So and that's called the GLM, or the generalized linear models. We call it linear because theta transpose x is linear, right? And we call it generalized because we generalize not just to two types of data types of y, but for more general kinds of y in general. Right? Okay, so let's get started with exponential families. Use a different pen. Exponential family. So the exponential family can be written in the form. So this is the probability density, PDF or PMF. So an exponential family distribution is a probability distribution whose density has the form P of y parameterized by eta equals B of y eta transpose T of y minus A of eta. Right? This is a cryptic looking expression. Let's add some color to this. So the data that we are on which probability is defined, let's call it y, y, y. All right, and the parameter of such a distribution call it eta, eta, eta. Right? So this is the Greek letter eta, and if you are using LaTeX, you use ETA, eta, to get that symbol. It kind of looks like n, but it's just an eta. So the parameter of the distribution is eta, and the support of the distribution, that is y. Now we call it y and not x because it's a hint. We are trying to model the output of our models with exponential families. So, so the probability density of y parameterized by eta is given by this expression, right? And there are kind of three functions over here. So we have b of y, and this is purely a function of y, and it's generally called the base measure, right? And we have t of y, this is called the sufficient statistic. And we have a of eta. A of eta is called the log partition function. Right? So, a few observations. The base measure, or the function b, is purely a function of y only, and it has no eta terms in it. Right? And similarly, the log partition function is purely a function of eta, and it has no y in it. Right? And similarly, t of y is again a function of y alone. And for pretty much most of this course, and most commonly, t of y will just be equal to y. I think of it as the identity function, but for most of the cases, t of y will just be y. And why are these called these particular names? So one way to think of it is the way an exponential family can be constructed is by starting with some base measure b of y, right? Assume it is some probability density, and come up with a new distribution whose density is So what's happening here? We have some base measure eta, and we can define a new distribution whose density is proportional to the density of the base measure times the exponent of the parameter times the data. To make this simple, let's consider a scalar case and where the base measure is. And now, because it's a probability density measure, if we normalize this, we'll have to to normalize this, P of y eta is equal to B of y times E of minus eta dot y over the integral of this with respect to y. Right? Integrate out y. P of y times E of minus eta y dy. Right? Does it make sense? So we are just defining a new probability distribution whose density is defined by the some base probability measure y times the exponent of a parameter times E of y, right? And then we just renormalize it. And this is also in some literature this is called exponential tilting. Right? And now what is this? This is B of y times E of minus eta transpose y. And this is just the expectation of e to the minus eta transpose y. Right? Does that make sense? This is just the definition. So this is the density, and this is some function, and you're integrating out. So this is the expectation, and this also happens to be called the anybody? It's a log partition function, but just this form alone is also called the moment generating function. Okay? But that's not relevant to our study here. So we can just call this some function of, let's call it capital A of eta, because you're integrating out y. The only variable here is eta, okay? And this comes in the form B of y times E of minus eta transpose y so I flip the sign here, this right, eta transpose y minus log A of eta. Right? Yeah.
Is there any way you know that B of y satisfies the properties of a distribution function?
Yeah. So the question is, should B of y satisfy the properties of a probability distribution function? In this form, it need not, because there could be some common constant that get cancelled between the two. So here you can actually think of it as some B prime, B prime, B prime, and B prime, and after you cancel the common constants, you end up with a B of y. But the main idea you want to think of here is, to get an exponential family distribution, you start with some base measure b, do an element-wise multiplication at each term with a e of a. You introduce a new parameter and multiply it by exponent of that parameter times y, and then just normalize it. And once you normalize it, what you get is it's called the exponentially tilted version of b of y, and that will be a member of the exponential family. Right? That's one way to think of how exponential family distributions are constructed, and kind of gives you a motivation of why it's called the base measure. So this is also called like the pre-tilted measure, and once you perform this process called tilting, you get a distribution in the exponential family. Right? All right. So that's just aside. That's just some motivation for why the names. You call this the base measure, and the partition function is another common name for a normalizing constant. Right? I think that term comes from statistical physics, where you use normalizing constants are called partition functions. And because this is a normalizing constant, and when you take it up here, you take because of the exponent, this becomes a log of a normalizing constant, and this is called A of eta, and therefore it's called the log partition function. Right? That's just some intuitions for why the names base measure and log partition function, why those names came into picture. But everything inside this box is not really relevant for our study as such. All right. So, and the claim is that a lot of probability distributions that we encounter, for example, the Bernoulli distribution or the Gaussian distribution, the normal distribution, and many more, they are all part of the exponential family. It means you can express these distributions in this form, right? And any distribution that can be represented in this form belongs to the exponential family. The only constraint is that the choices of B, T, and A should be such that this whole term is always non-negative and integrates to 1 when you integrate out y. Subject to those constraints, for any choice of B, T, and A, you have a distribution in the exponential family. Right? Now, any questions before we see how the Gaussian and Bernoulli belong to this family? Any questions with this so far? Yes, question. Go ahead.
Just a quick question. What is that symbol at the bottom? Something eta?
This one?
Yeah.
Oh, it's just a capital A. I just called it some, capital A of eta and use log capital A. This question?
So why are we dividing by the expected value?
Oh, so question is, why are we dividing by the expectation? So we divided by the integral of the numerator with respect to y, which will make it normalized to 1. So think of it as, so you have a set of numbers 1, 5, 7, and you want to maintain their ratios but still make them add up to 1. So you divide it by 1 plus 5 plus 7, 1 plus 5 plus 7, 1 plus 5 plus 7, right? And this makes them normalized into a probability distribution. They sum up to 1 now. So, and here we are doing the same thing for in a continuous scale, right? So integrate out the numerator and divide it by that integral. So this is called normalization. So you think of 1 plus 5 plus 7 as the different values this evaluates to for different values of y. Right? All right, so maybe to answer this clearer, so let's see what happens here. Now, we have some function b of call it b prime of y times e of eta times y. Now, let's assume this p of y equals this, and let's assume the integral of p of y is equal to integral of b prime of y times e of the eta times y is equal to some k, let's say equal to 100. Right? But now we want this to be a valid probability distribution, which means when you integrate out y, we want it to be equal to 1. Right? So what you do is you want to divide it by 100, so that when you integrate the whole thing, you get 1. Right? And this 100 comes because that's what you got by integrating it out in the first place. Right? So the integral of b prime of y times exponent of eta times y divided integral of y. Now, this term, the entire denominator is just a constant, and this will be equal to 1 over integral of b prime of y x of eta dot y times the numerator is integral of eta y, and you just cancel them and equal to 1. Right? That's you're just normalizing it such that the integral is always 1. Does that make sense? Yes, question.
Understood. So why did you times the exponential function here?
Oh.
Polynomial.
Yeah, so this is the process of what you call as an exponential tilting, and there are good reasons why you want to tilt something using the exponent function. There's a lot of theory of why the exponent is the right choice to do. Right? It's think of that as beyond the scope of this class. Yeah. Yes, question.
Is there any specific reason you cannot write down the transpose?
Oh, so here, just to give the intuition, we are considering eta to be a scalar in this case. So yeah, if this was a vector, then sure, think of this as. And then the integral would be, you would be integrating over y1, dy2, etc. Yes, question?
Yeah, I didn't quite understand how you got that the very first line.
The very first line? So this is the assumption we are making, where taking a base measure b prime of y, we want to construct a new measure such that the new measure is proportional to b prime of y times exponent of some parameter times y.
Is it like the separability condition, like when you found differential equations, you have a separability assumption or something like that? Like, why is it that that is a reasonable thing to, like what is the intuition behind why it would just be that?
So the intuition is that we're just defining a new distribution which is defined like this, right? And this is called, the tilted distribution, the exponentially tilted distribution. Okay? But the main point here is that, we went through this just to get a flavor of why the names came into picture, right? And we can go into details after the class. Come up to the stage. We can go into the details. But the main point is that if you can decompose a probability density into this form, into these components, then that distribution belongs to the exponential family. Right? Now let's look at a few distributions which actually follow this pattern. So let's start with the Bernoulli distribution. So the Bernoulli distribution, P of y parameterized by phi, is written as phi to the y times 1 minus phi to the 1 minus y. Right? This is the Bernoulli distribution, and the claim is that this form of the Bernoulli distribution can be rewritten in the exponential family form. Right? How do we do that? So the first thing we can think of is we can take the exponent of the log of phi to the y 1 minus phi to the 1 minus y. Right? Just took the exponent and the log. And the reason why we can take the log is because this is positive and this is positive, so you can take the log and then take the exponent again, right? And now we can rewrite this as exponent. So this will be y log phi plus 1 minus y log 1 minus phi, right? And this, we are rearranging terms, you get exponent. So I'm going to collect terms that have y in them to the left, and to the right terms that do not have y. So we will get log phi over 1 minus phi times y plus log 1 minus phi. Right? So all we have done here is pure algebraic manipulation. Right? we started with this form and brought it to this form. And now we can see, start doing a pattern matching, right? So the exponential family says P of y given eta is equal to B of y times exponent eta transpose y minus A of eta, right? Now we want to pattern match these two. So first thing we notice is that this is eta, so eta equals log phi over 1 minus phi, right? And this implies if we invert this, we get phi equals 1 over 1 plus e to the minus eta. And surprisingly and not coincidentally, this is the logistic function. And moving on, so we have eta equals this and phi equals this, and T of y equals T of y is just y in this case. Okay. So this should be T of y. T of y is just y. Okay. And A of eta. So A of eta is equal to minus, because A has a negative sign, minus log 1 minus phi. And if you plug in phi from this expression, A of eta will end up being log of 1 plus e to the eta. And B of y is just 1. Right? So we started with the Bernoulli distribution and did a whole bunch of just pure algebraic manipulation. Nothing more than algebraic manipulation. We didn't use any kind of logical deductions or anything like that, and just kind of massaged it into this form and did a pattern match to extract the corresponding B function, sufficient statistic, log partition function, and eta. And eta over here, forgot to mention, eta is called the natural parameter. Right. So yeah, so start with the density function, massage it into this form, and using pattern matching, just extract out the relevant terms of the exponential family. And so we have shown that the Bernoulli distribution belongs to the exponential family. Right? That's what we achieved. We showed that Bernoulli distribution belongs to the exponential family. Yes, question.
So phi was your parameter for success in this Bernoulli distribution, and then you find out phi. It got a function that you said was the G in our original distribution, like a logistic function. How does this phi relate to that G function?
So the question is, how does this phi relate to the G function that we saw in logistic regression, last class, right? Hold on a few more minutes, the relation will become clear. Right? Now, similarly, let's repeat this exercise for the Gaussian distribution. Right? So the Gaussian distribution has the form P of y given mu comma sigma square. Now we are just considering the univariate Gaussian, not the multivariate, and this will be 1 over square root of 2 pi times sigma exponent of minus half y minus mu square by sigma square. Right? This is the standard Gaussian distribution. In our case, we will be assuming a constant variance, and for the sake of derivation, we are just going to assume sigma square equals 1. You can leave it sigma square as some constant sigma square itself, and we will get the same results, but the derivations will look a little more complex. Yes, question?
When you're doing that comparison to get the different factors, how come the transpose on the eta disappears?
How come the transpose on the eta disappeared? Good question. Thank you. So in this case, eta is just a scalar. So yeah, when you have two scalars, transposing them is the same as just leaving it as it is. Yeah. Right. So here we're going to assume sigma square equals 1, which gives us a simplified version of the Gaussian. P of mu is equal to 1 over square root 2 pi exponent of minus half y minus mu square. And this we can see is expand the square and we get 1 over square root 2 pi exponent of minus half y square times exponent mu y minus half mu square. Right? So what happened here? Basically expanded the square, and one of the terms will have only y's, so got that out, and the other two terms are here. Yeah. And with this, we can again now do the same pattern matching exercise. P of y eta equals b of y exponent eta transpose t of y minus a of eta. And yeah, doing this pattern matching, we see that eta equals mu in this case. Eta equals mu, and similarly mu equals eta. The sufficient statistic T of y is just equal to y. Right. A of eta equals mu square over 2, and that's the same as eta square over 2. Right. And finally b of y equals 1 over root 2 pi exponent of minus y squared by 2. Right? Any questions in this? You can assume sigma squared to be some constant, and this is going to have a few sigma squares in a few places, but it's just a constant. And as far as constructing generalized linear models is concerned, that has no bearing. So we're just going to just to make the algebra simple, we're going to assume sigma square equals 1, and that's completely harmless. Okay. Any questions in this? Right. So and here we can see that from the point of view of exponential tilting, it kind of suggests that you get the Bernoulli if you start with a uniform distribution and perform an exponential tilting. And over here we actually see that for the Gaussian distribution, this is actually a standard normal distribution that has mean 0, standard deviation 1, and it's still a Gaussian distribution. Right? So for the Gaussian distribution, if you perform an exponential tilting, then you still get a Gaussian distribution with just different parameters. Anyway, that's just that's just to tie it back to the tilting interpretation that we spoke about. Now, exponential families have a few nice properties. Properties of exponential families. One property is that log p of y eta is concave in eta. That is, MLE is concave, which is the same as the loss function negative log likelihood is convex in eta, right? Another property is that the expectation of y eta is equal to so the first derivative of the log partition function is the expectation of the distribution. Right? This might look a little, why is this the case? We'll see. Similarly, the variance of y is the second derivative of the log partition function. And this might look a little surprising initially, but it should not be so surprising when we see the fact that the log partition function came from the moment generating function, right? And the moment generating function has the properties that as you keep taking derivatives, it keeps generating the moments of the distribution, right? So the first derivative of the log partition function, which is also the log moment generating function, gives the first moment. The second derivative gives you the second moment, and so on. Yes, question. Good question. What I was about to say is that you have these three questions as your homework question. So I'm not going to reveal a lot about that. And I think question number 4 in your homework 1 is you're asked to prove exactly these. So these are some very nice properties about the exponential family, and they're especially nice because in general, if you're given a distribution and asked to calculate the expectation, you are required to take the integral of something, right? You're expected to take the integral of your variable multiplied by the density, and if you want to take the calculate the variance, you're supposed to take the integral of the square of the variable with respect to the density, and in general, performing integration is hard. It's messy. It's not nice, right? But for the exponential family, instead of doing integration, you can actually just differentiate the log partition function. You differentiate it twice, you get the second moment. Right? Those are these are some nice properties about the log partition about exponential families. Any questions? Yes, question. Is this obvious, or is there a proof? It is. There is a proof, and your homework question number 4, homework 1 is you're asked to prove this. Why is it concave? It's in your homework. You need to show it. Yeah, all these are in your homework. Oh, NLL is negative log likelihood. So the maximum likelihood estimate is to calculate the maximum likelihood estimate. You take the probability, or the log of the probability, and you maximize this with respect to eta. Now, if you just switch the sign, you get the negative of this, and that's generally considered as the loss function, which you want to minimize. So, if in the maximum likelihood interpretation, you're trying to maximize something, and from a loss function perspective, you want to minimize something. So you just flip the sign, and and that's generally considered the loss function. Next question.
When you say concave, you always mean concave down.
What's can you please explain what's concave down and concave up? Oh, okay. Oh, I see. So the question is, by concave, do I mean this or do I mean this? Right? Is the function shaped like this or the function shaped like this? So the common nomenclature is when you have a global maxima. When there's a maxima, you call it concave, and when there is a global minima, you call it convex. Okay, so if you have a convex function, the negative of that will be a concave function, and vice versa. Good question. Any other questions? All right, so that's it about exponential families, and now we're going to see how the exponential family kind of ties into generalized linear models. So generalized linear models. So with the exponential families, so far we were dealing with y, right? The variable y. So we were defining a probability distribution over y, and the parameter was eta, right? And there was no x anywhere, right? In supervised learning, we're trying to learn a mapping from x to y, right? So in generalized linear models, we now use the exponential family to introduce a relation between a set of variables x to the variable y. And how do we do that? We make the following three assumptions, or these are like the three steps for constructing a GLM. So first is we make the assumption y given x belongs to exponential family with respect to eta, right? That is, given x and some theta, y now belongs to some exponential family whose parameter is eta, right? So far in this lecture, we didn't assume, but we were considering the cases when y belonged to exponential family parameter eta, but now we say y given x belongs to an exponential family with parameter eta. Right? And the goal of prediction will be to predict the mean. So the hypotheses that we want to learn is the expectation of y given x. Okay. And the third assumption that we're going to make is now connecting x theta and eta. So here we're going to make a reasonably strong assumption that eta will be equal to theta transpose x. Right? So these two seem somewhat reasonable. We're just assuming y given x follows some exponential family distribution. And also the second assumption was that the hypothesis or the value that we want to predict for an input x is going to be the expectation of this distribution. If in general, when you know that a variable is distributed according to some distribution, and you're asked to make a prediction of what value is, predicting the mean of the distribution is a pretty reasonable, value to predict. So this seems pretty reasonable. And then we make yet another assumption of the way we tie the parameter of the exponential family with the inputs as eta equals theta transpose x. Right? Now, together with these three assumptions, we can, or these three steps, we can construct exponential family or generalized linear models for different exponential family distributions. Now, let's see what happens. How do we construct kind of in a pictorial way? These three assumptions or these three steps can be kind of visualized like this. So we have some xi belonging to Rd. Right? Now we're going to run it through theta. I'm going to theta transpose xi, and that is going to output eta I, right? And this eta I becomes the parameter of some exponential family that has some particular sufficient statistic, log partition function b of y. By choosing the three different functions of an exponential family, you completely determine the exponential family, and the output of the dot product between theta and x become the natural parameter of that exponential family, and from this we sample yi. Right? This is the big picture you want to have in your mind. Okay? So, yes, question? So the question is, shouldn't these functions also be somewhat parameterized by the model? Yeah. So I would. The general process of how you go about constructing a GLM is to first choose a distribution. For example, choose that you want to model your output as Gaussian, or choose that you want to model your output as a Poisson distribution, or choose that you want to model your output as Bernoulli. And by making that initial choice of what distribution you want to use, these get fixed. Right? So these get fixed, the t function, a function and b function, they get fixed up front when we make the choice of the distribution for y. Right? And then the question becomes, what is going to be the parameter for a particular yi, right? And the parameter, the natural parameter, is then assumed to be theta transpose x for a given example. So theta transpose x will give you the natural parameter, and from this yi is obtained. So this is the assumption that we're going to make of how our data was generated. Right? Any questions about this? And so think of this as like the flow chart of the data generating process of how we believe the data is generated. A few things to note here is that theta is global. in the sense that you have just one theta for the full model, but whereas the parameter of the exponential family eta is different for each example. So each example, each x will output a particular natural parameter of the exponential family. Now we can now see how this relates to, for example, linear regression. So ordinary least squares or linear regression. This question. What's the question? Why is theta local to one family? No, eta. So the question is, why is eta local to one family? So the exponential family corresponds to distributions that have this form, right? Now, once you choose T, A, and B, you fix the functional form of your exponential family. And by, for example, by choosing your B, T, and A according to that set of choices, you get the Gaussian. By choosing B, T, and A according to this set of choices, you get a Bernoulli. Right? So now if I understood you correctly, the question is theta is local to x. Is that a question?
No. Theta is because theta is a linear function of theta and x. Right?
Yes.
Is it local to your data or is it local to your model?
I'm kind of trying to understand what you mean by local to your data or local to your
distribution.
Yeah.
Your eta will change.
Yeah, so eta is, you get a different eta for different examples. So each example will output its own eta. Right? So in this process, xi, take a dot product with theta, will give you eta I of the ith example. Yes, question?
So is it going to be like for every example, Gaussian is moving across the whole thing?
Exactly. We'll I'm going to draw a picture about that in shortly. Right? So so for the ordinary least squares, if we make the choice that our exponential family is Gaussian, then a natural consequence of that is, so if you construct a generalized linear family where the exponential family distribution is Gaussian, then you naturally get least squares regression is what you should be doing. Right? Why is that? So assuming exponential family is Gaussian, we get h theta of x. We want h theta of x to be the expectation of y given x theta. And we saw that the mean of Gaussian is just mu. Right? Mean of a Gaussian is mu, and mu as a function of eta was just eta. Right? And eta is equal to theta transpose x. So we basically get h theta of x equals theta transpose x. Right? And that was our hypothesis for linear regression. Similarly, for logistic regression, so logistic regression is again basically a generalized linear model where we choose the exponential family to be Bernoullis. Right? But by just making the choice that the exponential family is Bernoulli, logistic regression pops out as a natural consequence. So, again, so assume exponential family is Bernoulli. H theta of x again should be expectation of y given x parameterized by theta. And in case of Bernoulli, the mean of the Bernoulli is just phi. Right? And phi as a function of eta, what we saw is equal to 1 over 1 plus e to the minus eta. And then we make the third assumption about GLMs was that eta equals theta transpose x. So 1 over 1 plus e to the minus theta transpose x. H theta of x equals this. Right? And what we see here is that this is exactly equal to g of theta transpose x, where g of z equals 1 over 1 plus e to the minus z. Right? When we introduced logistic regression, we arbitrarily chose g to take this form, something that squishes minus infinity to plus infinity into the range 0 to 1. But this is a more principled way of deriving it, where you think of your output to be following a Bernoulli distribution and construct a GLM, and with just those two assumptions, we see that our hypothesis must take this form. Yes, question? Was there a mathematical reason for our third assumption? So this is a modeling choice where you're making an assumption that the natural parameter is a linear combination of your x's. You can make this relation as complex as possible in general, right? Beyond GLMs, you can, for example, say your eta equals some neural network parameterized by some theta of your x, right? And this is totally fine. You can construct generalized models, except now it's no more linear. You can't call it GLM, but you can absolutely do something like this. But for GLMs, it's a linear model because we are making the assumption that eta is a linear function of x's. So the question is, GLMs are convex or concave, and when you look at your scatter plot of your data, if it does not look convex or concave, should we still fit GLMs to that data? Right? One thing to note is that the GLMs and exponential families are all convex or concave with respect to the parameters, and in a scatter plot, you're looking at data. Right? They're two different things. Right? Now, your data is generally kind of embedded in your loss function in some way. It's kind of, the shape of the loss function is decided by your data. And the shape of the loss function is going to be very, very different from looking at the scatter plot of the data itself, right? Your data may look in any shape or form, right? But that tells you nothing about how the shape of the loss function is going to look. So maybe the next diagram I'm about to draw might answer your question. If not, please ask the question again. Yeah. So here we see that the linear regression and logistic regression pop out as natural consequences, by just choosing, by just making the choice of our exponential family distribution, right? And now, how does this kind of look visually? So for linear regression, so for linear regression, assume this to be your x-axis, the data, right? And there is some theta that, so x is in RD, theta is in RD, but for this picture we're just assuming it's one dimensional. And here, this line, for example, right? This line is basically eta equals theta transpose x for some theta, right? And then what we saw was eta for, in case of the Gaussian distribution, is also equal to mu. Right? For the Gaussian distribution, eta equals mu, and y for a given x is now distributed as a Gaussian with mean mu. So if we take the example xi, we get a mu I, which means for this value of x, we assume that centered around here we have a Gaussian distribution, right? So this is y, and this is xi, and from this Gaussian distribution we sample a y. Let's say we got this one, and this is yi. Similarly, for a different, say, xj, there's a Gaussian distribution, and from this Gaussian distribution we sample, let's say, this is yj, right? So for every different value of input, for every input value, for every x, we dot it with theta, we get eta, and that eta is equal to mu of a Gaussian distribution centered at that eta or mu, and from that Gaussian distribution, you know, it's a distribution along this axis. We sample a y, right, and that makes the xi yi pair or the xj yj pair, right? So let's look at a few more. There is another Gaussian distribution here. For this point, let's assume this. For this point, this, right? And from this, we assume that the data is generated this way. From this we get, this is x, this is y. So I'm just going to try to draw those points again. Right, so this is x, this is y. The data was generated, so this is the data generation process. And now when we start our machine learning analysis, we start from here, right? This is the observation or the data. Right? And from this observation, we now want to infer what theta is. Right? So each point over here has, you know, so the true theta might be something like this, but we don't know. Each example, each yi has two parts, right? So each of these is basically theta transpose x plus epsilon, where epsilon is the Gaussian noise. So theta transpose x, think of this as the signal and you have a noise, and you're trying to separate the signal from the noise, right? We want to get what the signal is. What is theta? What is the invisible dotted line over here from which the y's are sampled, right? And the way this relates to generalized linear models is that we assume for each example there is an exponential family distribution, in this case the Gaussian. For each example there is a Gaussian distribution, and the y was sampled from that Gaussian distribution, right? And now by just starting with the x and y pairs without seeing anything else, we want to learn what theta is, and that's where that's basically statistics, machine learning, right? You start from the data and you're trying to construct what the model is. Yes, question. So the question is, in practice, how do we know whether the noise actually follows a Gaussian distribution or not, right? And the short answer to that is, it might sound funny, but in machine learning we don't care, but in statistics you care a lot, because in machine learning our goal is, are we able to learn a model that that just does well in terms of prediction on unseen data, right? Whereas in classical statistics, we are trying to, your data is kind of hopefully generated with a well-designed experiment where if you perform a regression analysis, the values of theta are meaningful in some way. You can test a hypothesis, right? And over there, the assumption of whether the noise was actually Gaussian or not are very important, right? But from machine learning point of view, we are mostly interested in how well our model predicts on unseen data. For example, if yi is, if there is a new test example x star, our model, suppose it learned this other line to be the hypothesis, then it's going to say this is going to be your prediction. And the so in general we are interested in what is this gap basically, right? And in practice it's not even possible to measure this gap because we don't know the first dotted line, right? So so we're going to make this prediction, but the true data was sampled from from a distribution centered on the first dotted line, so your data might be here, and what we care is how far was our prediction from the observed data, and that's all is our focus in machine learning. We are not trying to we care less about what was the specific value of theta, is it meaningful, those are questions that's more classically handled by statistics and not machine learning. Good question. Yes, question.
So let's say you make a certain initial assumption, and then you'll get different models, and different models give you different accuracy. You have financial stakes in what the prediction is.
Yeah.
It will matter a lot what you made your initial assumptions to be.
Yeah.
So can we have like a mathematical maximum likelihood kind of thing, which tells us, given this data, which is the most likely distribution or assumption that we should make?
Right, so I guess to summarize your question, is there a more principled way of choosing what our distribution should be, right? The short answer there is, so in machine learning, when we are given a set of data, right? Let's assume you have some training set, right? Generally, what we do is we split it into a training set and a validation set and a test set, right? And for questions such as the one you posed about what's the choice of the exponential family distribution we want to make, the answer almost always is going to be try both approaches, try two different distributions, say Gaussian and Laplace, and see how well that performs on the validation test, on the validation set, and whichever of the choices work better on your validation set, go with that. Yes, that's just a limitation that we live with. Yeah, exactly. Yes, question.
In the non-generalized version of linear regression, we would see y as the true values that we have, like the labels one we are sampling y?
Well, so the question is, here we are sampling y. The sampling is the assumption that we are making of how the data was generated under the covers.
Okay, so we are predicting the distribution by sampling y.
So what we are predicting is, so with linear regression, we saw two different interpretations, right? One was just minimize the cost function, take the data that we have, minimize the cost function. The other was the probabilistic interpretation, right? And right there we had made the assumption that your yi was sampled from a normal distribution whose mean was theta transpose x, right? And we are making that assumption, which may or may not be true. And if we believe in that assumption, then the maximum likelihood principle tells us that we need to minimize the squared loss. Right? And similarly over here, if we make a generalized, if we assume that our data is from a generalized linear model where the exponential family is Gaussian, then our hypothesis should be, maybe I erase it. Our hypothesis should be just theta transpose x, which is basically the linear regression hypothesis. And if you perform maximum likelihood expectation on your generalized linear model, then you get the squared loss as well. Right? So the linear regression and logistic regression are exactly specific cases of generalized linear models where we chose the family exactly. By making a choice of the family to be Gaussian, we get exactly linear regression. By making a choice to be Bernoulli, we get exactly logistic regression. Right? So that's this is the picture you want to have in mind for linear regression. That the assumption is that there is some theta, some true theta, which acts as the mean for each yi that we're going to sample from, and the yi's that we're going to observe are going to be sampled from this. So there is some noise coming in, and we start with these noisy observations. And we are, the hope is that we kind of, prune away the noise and can extract the signal in there, right? That's the picture you want to have. And similarly for logistic regression, yes, question. Yeah. So we don't get a theta. When you start your machine learning task, you're just given your data set, your x's and y's, right? And then we make an assumption that the way the data was generated was through a generalized linear model. If we make that assumption, then the set of actions we need to take is to perform maximum likelihood on a generalized linear model. And if the generalized linear model has a Gaussian distribution, then you get linear regression. We don't generate y's. We just take the observed x's and y's and start from there. Exactly. We don't sample. We don't do any kind of sampling as part of our analysis. I'm sorry. Can you please repeat that?
Infer theta each step, and you will compute the noise with the infer theta, and then compute the signal given these two steps.
So effectively what we are doing is we are trying to estimate what theta hat is. We try to come up with an estimate theta hat that is as close as possible to the true theta. That's essentially what we're trying to do. Right? The output of our model is always some parameter vector theta. Like for example, you do linear regression, say use the normal equations. The output of the normal equation is some theta hat, and that's our estimate of what the slope was. Right? So for logistic regression, the picture looks again somewhat similar. So this is x, and assume this is eta equals theta transpose x, right? And now we have yet another function which is the activation function. Oops, I messed this up, sorry. this is y equals 0 and y equals 1. Right? So for the logistic regression again, this is phi equals g of eta equals 1. Right? Again, for logistic regression, assume x is our data axis. For simplicity, we are just drawing it as one dimensional, but in general, this is in d dimensional, right? And eta equals theta transpose x is this, hyperplane or a line in one dimension, right? And what we then have in case of linear regression, eta was mu, but in case of logistic regression, phi, that is the mean, is not equal to eta but g of eta, where it takes this form. This is basically our logistic regression hypothesis. Right? This is also h theta of x for logistic. And now the way the way the data is generated, the way you want to think about it is that for any given value of x, right, calculate g of eta. This is the phi or phi I corresponding to xi, and from this phi I, sample a y. Right? Now, if it is close to 1, if the mean of the Bernoulli is close to 1, then it's more likely that you're going to sample a 1 instead of a 0. So, for example, here we might get here, and for this again might get here. This might here, here. Maybe one of them might be here, and similarly for low probabilities, for those regions of x where g theta of x will be a low probability, you're mostly going to get things here, and maybe occasionally one of them will be here. And for the region where your h theta of x is close to 0.5, you would expect roughly an equal number to be both up and down, right? And from this data generation process, we get a data set that might look like this: x and y. So So you might get a data set that looks like this. Again, this is just visualized in one dimension. And from this, we want to now work backwards towards the theta that gave rise to the hyperplane, which then gave rise to this logistic function from which the data was sampled. Right? Does that make sense? From here, we want to then backwards and ask what was theta. So there are any questions on this? Yes.
You said that in the model theta was mu. Are you implicitly assuming that there's a Gaussian distribution on the noise as well?
So I said in case of linear regression, eta equals mu precisely because we made the Gaussian assumption. All right. So a few things to kind of keep in mind. There are lots of parameters moving around here, right? So we have eta, we have mu's, we have phi's, we have thetas, and it's it's quite easy to kind of get lost in all these different parameters, and so it can be useful to have a big picture of where the different parameters kind of lie and what role they play and what's their relationship with each other. So we have model parameters. And then we have the natural parameter. And then we have mean parameter. Right? So theta in RD is the model parameter. Eta I is the natural parameter, and the mean parameter is going to be different for different distributions. For example, if it is mu for Gaussian, phi for Bernoulli, lambda for Poisson, and whatever it could be. And the choice of the distribution implicitly chooses which mean parameter we are working with, right? And the relation between the model parameters, which must the dimension must match with x, the model parameters dotted with x give the natural parameters, right? So we have theta transpose xi gives the natural parameters. So that's the relation between your model parameters and the natural parameters. And the natural parameters is 1 per example, right? And then from the natural parameter to the mean parameters, we have something called the g function. So the g function takes us from natural parameter to the mean parameter. In case of Gaussian, g equals just g of. In case of Gaussian, g of eta is just equal to eta, and similarly in case of Bernoulli, phi equals g of eta equals 1 over 1 plus e to the minus eta, and so on, right? And this function, the function g that takes you from the natural parameter to the mean of the distribution, is generally called the canonical response function. And the canonical response function has this property that it will always have an inverse, right? It's always an invertible function. And the inverse, which takes you from the mean back to the natural parameter, is generally called the canonical link function. It's generally called the canonical response function because generally y is also called the response variable sometimes. And so it is taking you from etas to like the mean of your y. So it's also called the canonical response function, and the canonical link function is basically the inverse of it. And the thing you want to keep in mind is that there are 3 different kinds of parameters we can talk about. So the first is the thetas, and when you perform gradient descent to perform maximum likelihood on your Gaussian or on your generalized linear models, these are the parameters that get trained, right? These are the parameters that we are adjusting in each step of gradient descent or stochastic gradient descent, right? And once you fix these, the natural parameters are just the output of theta transpose x for different values of x's. So these are kind of ephemeral in some way. We don't store them, whereas we train and store the theta parameters, right? And the natural parameters are just the output for different values of inputs, right? And then you take them through the canonical response function, and you get the mean of your y variables. And this is the prediction that we do, right? So the prediction is h theta of x equal to the expectation of y given x theta, and this is always g of theta transpose x. Yeah, so are there other kinds of generalized linear models? That's the next thing we're going to discuss. Right? So we saw two examples for generalized linear models, classification and regression, and let's see let's see a few other types of GLMs. So in order to first construct a GLM, right? In order to first construct a GLM, the first thing that we do is first look at our data, right? You're given pairs of x and y's. The first thing you want to do is look at your y and find out what data type it is, right? Your y variable might be binary, just zeros and ones. It can be real valued, which means it can take a value between minus infinity and plus infinity. It can be counts, which means it exists only as integers, like counts of how many clicks is my website going to have, or count of number of customers who are going to walk in through the door. Right? It could be just counts. It could be multi-class, discrete, and in the sense if you're trying to perform classification of whether a given image is, I don't know, a cat or a dog or an elephant. Right? It can be discrete, but and not binary, but a set of classes. Right? And it can also be just positive real valued. For example, if the y value is the time until some event happens, then it's real valued, but just limited to positive values. Right? So the first thing that you want to do is look at the data type of y. Right? And supposing the data type of y is real valued, then the next thing you want to do is make a choice about which exponential family distribution you want to use that has a support compatible with your data type. Right? For example, if it is real value from minus infinity to infinity, look up the table of exponential families, say on Wikipedia. Wikipedia's page of exponential families gives you a table of all exponential family distributions, and look at those that have support equal to the full real line, and those are all eligible options for you, right? So for example, you can choose Gaussian, or you can use Laplace, right? And there may be a few more, right? But they need to be limited to the exponential family. And when your data type is real valued, then the name that we give it is regression. Okay. Similarly, if it is 0 or 1, then we choose Bernoulli and we call it classification. Okay. For the choice of Gaussian, we got linear regression as our algorithm. For choice of Laplace, you're going to get a different algorithm, but it's still a valid algorithm. For Bernoulli, we got logistic regression. Now, it could be 1 through k, and here it can be categorical distribution, and we call that multi-class classification. If it is natural numbers or counts, and one example could be Poisson. This is there in your homework. So in your homework, question 4 or question 3 or something, you're going to construct a generalized linear model for Poisson. Take a data set, fit it, make predictions, etc. And you call this, either count regression or Poisson regression. Similarly, if it is positive real values, and specifically if it is like, if your y variable is timed to some event, then you have choices like exponential. So the exponential distribution is distinct from exponential family. The exponential distribution is a member of the exponential family. It may be confusing, but there's the exponential distribution, not the exponential family. Exponential, or you can use gamma distribution. There are a few more. And generally, when you're trying to predict the time to some event, you call it survival analysis. Right? And you can also have your data type to be probability distributions themselves. So this may be a little advanced, but if you're doing Bayesian statistics, for example, you can define a probability distribution over Bernoulli distributions. In which case, the exponential family for Bernoulli would be a beta distribution, and you can give it some name. Similarly, your y variable can be a categorical distribution itself, in which case you want to have a distribution over distributions, like for example the Dirichlet distribution, and all of these can be fit in to the generalized linear model framework. Right? You start with what your y variable is, data type of y, and the data type of y is going to inform the choice of distributions that you can use. Right? So if somebody, if you're wondering, is generalized linear models used for regression or for classification, the answer is it can be used for anything. Just use the appropriate choice of exponential family distribution. Right? Any question? Yes. I'm not going to go deep into that. You can ask me after the lecture. I can explain more. Right? Any questions? Now, what did we gain by putting them all in a common framework? Right? We saw that yes, it's kind of mathematically elegant to kind of put them all into a common framework, but have we gained anything as such? Right? The answer is yes, we have actually gained. Once we make a choice of distribution, we can go through the exercise of algebraically massaging it and doing a pattern matching to find out what our g function is. So first thing you want to do is make a choice of distribution according to the data type. Now, and for that distribution, express it in exponential family. Exponential family, which means find out what is A, what is A of eta, B of y, T of y, and most importantly, your mu or phi or the mean parameter, express it as a function of eta, right? So calculate the g function. Right? That's the most crucial part, right? And this g function will decide what your hypothesis is. So the hypothesis h theta of x is now g of theta transpose x. Right? And probably the most useful benefit of going through of building a GLM is that once you do this, in order to perform maximum likelihood estimation, you don't really need to write out the log probability, take the gradient, and derive an update rule. The update rule for all generalized linear models is the same rule, and that rule is theta equals theta plus some step size alpha times yi minus h theta of xi times xi, right? We've seen this update rule over and over, and what you can see is if you start for any generalized linear model, for any choice of the distribution, you take the log probability, perform maximum likelihood estimation to get the gradient, and the update rule that you end up with will always take this form, right? So in case of logistic regression, your yi's are zeros and ones, your h theta is, goes according to this, and for linear regression, your y's could be are real valued. For Poisson regression, they're going to be counts. But no matter what data type you have, the update rule that you're going to end up with is always the same. Just that h theta of x will be different according to the choice of g. Right? And finally, for prediction, right? Prediction y hat is always h theta of x star, and this again is equal to g of theta transpose x star. Right? So basically, with GLMs, not only do we have a nice and elegant unifying theory, but it also gives you an update rule that you can go directly without writing out the log likelihood, without taking the gradients. You can just go and start using this update rule and and run it till your model converges. Yes, question. That's a very good point. So the question is, when we use this y hat, according to this, then our prediction that we are making will not lie in the support of the data type, right? That is true. And for example, for logistic regression, the hypotheses will output a probability value, right? And then it is up to us to choose some kind of a threshold to say, anything above this threshold, we classify it as positive, and anything below, we classify it as negative. And similarly, even for Poisson regression, right, your data types are going to be counts, but the value that comes out of this is going to be real valued, right? Again, in which case you can either round it to the minimum, to the nearest integer, or you can just sample from the Poisson. You can do something like that. Exactly. Yes. Question.
Just reading the board question. The symbol on the x-axis with the indices.
This one? Yeah.
No, on the last row.
This one? This was just x star, just to say it's some test example, some unseen example. So, yes, question. So the question is the threshold that we want to choose to decide whether the output of a logistic regression was 1 or 0. Can we adjust that threshold? Yes, you can adjust that threshold. It's generally it's generally a post-processing step, which means you fit the model as it is, and after you fit the model, on a validation set, you can decide what threshold you actually want to use. You don't always have to use 0.5. You can use a different threshold. It's generally not something that you learn from the training data. So the threshold is not something that you learn from your training data. The threshold is something that you tune on a validation set. And we'll probably cover. We're going to have a lecture on evaluation metrics in one of the future lectures, and there we're going to talk about thresholds and things like that. All right. So moving on. The last topic I want to cover today is softmax regression. Softmax regression. So softmax regression is again a type of it is part of the exponential family or a generalized linear model. When you make a choice of categorical as your as your choice of exponential family, you get multi-class classification, and this is also called softmax regression. So the lecture notes has a pretty detailed. It walks you step by step of how you actually construct softmax regression as a generalized linear model, and I highly encourage you. You need to kind of go through that in the lecture notes to kind of go through the mechanics of it. But during the lecture instead, I want to provide some kind of some intuitions about how softmax regression works, so that what you read in the lecture notes, which is pretty heavy on notation, so that it makes a little more sense. Right? So softmax regression is for multi-class classification. Okay. And let's start with some pictures. Right? In case of x1, xd. Okay. In case of logistic regression, we started off with two classes. Let's say this is class 1, and then we have another class over here. Call this minus. These are some examples. Right? In the picture we drew for the generalized linear model, we just had one dimension for the x-axis, and y was on the other dimension. Over here, this is x1 and xd, and the y or the label is basically embedded in the shape or the color over here. Right? And then our goal was to come up with some theta such that theta transpose x equal to 0, this line would act as a separating hyperplane. Right? That was logistic regression. And theta transpose x greater than 0 was like the positive classes, and theta transpose x less than 0 was the negative classes. This assumes that p of y given x theta equals 0.5 is the separating hyperplane. So if you assume 0.5 is the separating probability, then the theta that you learn has this property that it's the separating hyperplane on one side, where it's greater than 0, you classify it as positive, and the other side is negative. Right? Now, what happens in case of multi-classes? Right? What if we have multiple classes? x1, xd. Okay? Let's assume there's one class over here and another class over here, some examples over here, and let's use another color and say some examples over here. Right? And let's say these, let's say this belongs to y equals 1, y equals 2, and similarly whatever y equals k. Right? We have k different classes living in a d-dimensional input space, right? And we want to now build a multi-class classifier. So the first thing we want to change from this view is, first we want to figure out where is the theta vector. Right? So in this case, the theta vector will be like this. Right? So this is the theta vector, right? Because any vector which is less than 90 degrees from theta will give you a dot product that's positive. Any vector that is more than 90 degree will give a dot product that's negative. Right? So this is our theta vector. When we move on to multi-class classification, here we will now have one theta per class. Right? So this I'm going to call it theta 2. This would be theta 1, and let's call this theta k. So for every class you get your own theta vector, right? And over here it was clear. So if theta transpose x was bigger than 0, it was one class. It was less than 0, there are other class. But now we have multiple theta vectors, and the way we're going to classify something as belonging to one class is to take that input vector x, right? Calculate theta 1 transpose x, calculate theta 2 transpose x, and so on until theta k transpose x, right? Each is a scalar, and pick the corresponding k for which the theta k transpose x is the largest, right? So each of these is in R, right? And from this what we want to do is to take the max, or rather the argmax, as the predicted class. The intuition to have there is that for the set of examples that belong to a class, the theta k is kind of pointed in that direction, so that only those examples belonging to that class will give a dot product with this vector to be much larger than their dot products with the other thetas, right? For example, for pick this blue, right? The dot product between this example and theta k, because they are so well aligned, is going to be much bigger than the dot product of this with, say, the red, because in fact this is greater than 90 degrees, so this will be a negative value, and similarly the dot product between this and the black vector will be negative value, but between the blue vector it's going to be positive, and so the class k will win out as the max, right? And this set of thetas, we want to write it out in a matrix form. Right? Where each row is d-dimensional, and you multiply this with a vector x, which is also d-dimensional, right? And this will give you, and you have k such vectors, right? You have one theta vector specific to each class, and you dot it, you get a real value. And for some example, let's call it xi, the different theta transpose x's might look like this. So for I equals 0, for class 0, you might get theta transpose x. For class 1, the dot product might be negative. For class 2, again the dot product might be positive. And the way softmax regression works is to take the set of these scalar valued dot products and convert them into a probability distribution. Right? Now, given a set of scalar valued numbers, how do we now convert this into a probability distribution? So for a probability distribution, there are two properties. The first thing is that all the values should be non-negative, and the second property is that they should sum over to 1. Right? So the first thing we do is make them all positive while still maintaining the relative orders. And and can you suggest one way how we can convert all of these into positive values while still maintaining the relative orders? You can add a constant, very good. Another way is to, I'm sorry? The absolute function will make it positive, but it might not maintain the order. For example, a highly negative one might become might become larger than. You can use a sigmoid function, very good. The sigmoid function will squash everything between 0 and 1. A simple technique is to just exponentiate them, right? So exponentiate each xi transpose theta I, and this will now make them all positive. So if the input to exponent is minus infinity, it maps it to 0. If it's highly negative, it maps it to a very small positive number. And if the value is positive, it will make it much more positive, right? And then we normalize it. We normalize it such that the heights add up to 1, right? And how do we normalize it? Dividing it by the integral if this was continuous. In case of discrete, you sum them up and divide them, right? And you get, I'm just going to continue it here. So you get exponent of x transpose theta I over summation over j exponent of x transpose theta j, and this will be probability that y equals I given x theta. And this function is called the softmax function, right? The softmax function takes a set of scalars, real valued scalars, and converts them into a probability distribution, right? Where the larger valued scalars will have a higher probability, the smaller valued scalars will have a smaller probability, and they all add up to 1. Right? That's the softmax function. All right, any questions? Yes. Can I write a little bigger? Sure. Sorry about the writing. So maybe I'll just write it a little more clearly here. Probability y equals I given x theta is equal to exponent of x transpose theta I divided by the sum over all j exponent of x transpose theta j. Is that clear? Right, so this is basically the softmax function, and the reason why it's called softmax function is because if you're given a vector x and you want to extract the maximum value or of the largest component of x, one way to do it is to do x transpose softmax of x, and it will give you something that is similar to the max, the largest component of x. And this is differentiable. You can do gradient descent, etc. And it's a differentiable, smooth way of extracting the maximum value of maximum component of some x. So that's why it's called the softmax. All right, that's about it in terms of generalized linear models. This is the big picture you want to have in your mind, and exponential family, which we already discussed, and generalized linear models take exponential families and relate it to some input x with the assumption eta equals theta transpose x. That's the big picture. All right, thank you.